Good morning, Year 10. This is Miss Teresa. Today, we'll be talking about critical angle and total internal reflection. Our lesson objective for today is to discuss critical angle and total internal reflection, and success criteria. I can analyze the conditions for total internal reflection, and I can describe the relationship between critical angle and refractive index. Let's just have a quick recap about refraction. We know that refraction is the bending of light rays from one medium to another. How the light bends depends on where it comes from. When the light originates from a less dense medium to a denser medium, in this case from air to glass, it bends towards the normal. This is because it slows down. When the light comes from a denser medium to a less dense medium, let's say from glass to air, then it bends away from the normal. This is because it goes faster. With that in mind, let us analyze the bending of light in the following situations. Let's assume that a light ray can originate from inside the glass at a 25-degree angle. As it goes out of the interface, it bends away from the normal at an angle of 39.2 degrees. Then we increase the angle of incidence to 30 degrees, and we get an angle of refraction of 48.6 degrees. When we use 35 degrees as an angle of incidence, we also get an increased refracted angle of 59.3 degrees. As we increase the angle of incidence to 40 degrees, the angle of refraction is correspondingly larger, with a measure of 74.3 degrees. Now we can see a pattern of increasing refracted angle. But there comes a special angle. The special angle for glass is 42 degrees. Why is it special? Because the angle of refraction will look like this. The angle of refraction is now 90 degrees from the normal. This is called the critical angle. What is critical angle, you say? The critical angle is the angle of incidence which produces an angle of refraction of 90 degrees, which is a refracted ray along the boundary of the surface. The critical angle differs from one material to another. It is specific to that kind of material, and it will never change in any kind of situation. The critical angle, denoted by the capital letter C, is related to the refractive index of a transparent material by the equation Ri is equal to 1 divided by sine of the critical angle. Or other people use N for refractive index is equal to 1 divided by the same sine of the critical angle. So these are the equations related to critical angle and refractive index. Ri is the refractive index of the material and C is the critical angle. Okay. Now, using that equation, let's solve for the critical angle of some materials. Let's say crown glass. Crown glass has a refractive index of 1.5. So we know that Ri is equal to 1 divided by sine of the critical angle. But we're looking for critical angle C, therefore we're going to rearrange this equation. It will become sine C is equal to 1 divided by the refractive index. Now, this is the new equation. We only need the angle C, not the sine of the angle C. Therefore, we're going to use the inverse sine of that. So C now is equal to the inverse sine of 1 divided by the refractive index. So this is the angle, critical angle. This is the formula that we can use for finding the critical angle. So let's solve for crown glass, which is like 1.5. So C now is equal to the inverse sine of 1 divided by 1.5. Okay, so let me solve in my calculator. 1 divided by 1.5 is 0.67, and then I'm going to get the inverse sine of that, which is equal to 41.8 degrees. Now roughly that is actually 42 degrees. Therefore, this is the refractive index of ground glass, 42 degrees, using C is equal to the inverse sine of 1 divided by refractive index. This is the formula I used. Now you're going to solve for the others. Water, critical angle of water, critical angle of perspex, sapphire, diamond, and germanium, using the same formula. You're going to write it in your notebook and then you're going to submit to me. So what's the significance of the critical angle? Why is it critical? Because if we use an angle of incidence greater than the critical angle, there will be no refraction to happen anymore. Instead, something else will happen. When the angle of incidence is greater than the critical angle, total internal reflection occurs. All light is reflected at the boundary. Let's say we have an incident light ray at 45 degrees, which is higher than the critical angle of glass. Instead of refracting, it will reflect inside the medium itself. Hence the name total internal reflection, because all the rays will be reflected internally. The same will happen if we have, let's say, an angle of 50 degrees. This is 50 degrees. Instead of refracting outside into the air, it will be totally internally reflected, and it will follow the laws of reflection, which is angle of incidence is equal to angle of reflection. So this is 50 degrees, and this should also be 50 degrees. And if we are going to use 55 degrees, the same thing will happen. Okay, this is 55 degrees. Instead of being refracted, it will be reflected internally, and then it will be 55 degrees also in that medium itself. But total internal reflection only happens under two conditions. One, light travels from a dense medium to a less dense medium, example, from glass to air. And the second one, the angle of incidence in the dense medium is greater than the critical angle. So those are the two conditions for total internal reflection to happen. So what have we learned today? We analyzed the conditions for total internal reflection, and also we described the relationship between critical angle and refractive index. I hope you enjoyed the lesson today. This is Miss Teresa signing off. Have a nice day.